flow with the fuel may be turning, maybe it's rotating this way, so moving this way axially, but rotating also around. So this is, let's say, a low axial speed, which is very good, and turning like this, it will help in atomizing the fuel and in getting, in fact, the fuel that is, let's say, under the form of very small droplets. And in this zone, what will you do? You will create the droplets and you will also vaporize the fuel so that these droplets are becoming much smaller, and at the end, so you have, in fact, only gas that is mixed with the air, fuel gas that is mixed with the air. So a first problem to solve is the problem of the speed. Let's call it the Mach, or let's call it the speed. This is the same. You need to reduce the speed, and we will take care of that by building the combustion chamber with these two walls, and only a small speed is existing in this zone where you have the flame that will be created. The second problem you have, this is that the fuel to air ratio that we have in the combustion chamber, globally speaking, this is the fuel flow divided by m dot. This is in the region of 1 divided by 60. Whereas the stoichiometric fuel to air ratio that you should have in order to have a rapid ignition and a good combustion of the mixture is something like 1 divided by 15. So you see a ratio 4 between the two. And so what will we do? We will create in the recirculation zone, we will create the stoichiometric fuel to air ratio. And so, I mean that only, let's say, 25% of the air will be present here. So, with the flow entering through this side, entering through this side, entering coaxially with the fuel, you will have only 25%. And the rest will be added gradually later on with, let's say, normal or perpendicular entrances, but also because now you have created the flame, so here you have the flame, you need to cool down this flame tube, and what will you do? You will also create things like that. So you will create openings like this, so that you are sending a part of this flow also tangentially, so that you are creating a film of air that is cooling, that is protecting the inner side of the combustion chamber. And so globally speaking, you will have here less and less air. So the amount of air that you have here is decreasing because you are diluting the flame with this and protecting the flame tube with the cooling air. And at the end, what will you do? What do you need to do? You need again, of course, at the end to reduce the size. So you see that here the exit section, the section, let's say A3 of the combustion chamber, must be again small. Why? Because here behind you have the turbine, and the turbine needs a large speed. So you see that the combustion chamber is a divergent convergent with, let's say, a kind of constant section area in the middle. If you want, you can call this section the section A3 prime, and you see that the combustion chamber is going from A2 to A2 prime, large increase to A3 prime, constant section, A2 prime is equal to A3 prime, and then again a convergent path in the exit. And you will understand why later on. We can have combustion chambers that are closing like this. So you have only, let's say, hot gases, m dot plus m dot f, that is exiting, but you can have also combustion chambers that are like this. You can have combustion chambers that are like this, where there is still air flowing here, air flowing there, and where you have the m dot that is here, m dot plus m dot f, of course a part of m dot, because there is also a part here. And so, of course, this air is rather hot, because it has been reheated with the inner part of the combustion chamber, and you are going to the turbine with a part of the exit flow of the combustion chamber that is hot but not very hot, and the central part that is extremely hot. So the temperature here is higher than the temperature there, is higher than the temperature here. We will discuss that. Why are they doing that? We will see that in a minute. And I will show you this flame tube, this famous flame tube. This is something like this. So you see, the fuel is entering through here. So there is the injector of fuel that I will show you later on, that is here. So a pipe of fuel, and the fuel liquid is entering into the chamber with the injector that we will discuss later on. A part of the air of the 20% is entering through here. So coaxially, maybe with a swirl that we will discuss later on, that gives you a rotational movement so that you decrease the axial velocity, so decreasing again the speed of the air. And you have these holes, like you have here, that are bringing the air normally through here and through there, and creating in the section here inside a recirculation. And you have larger holes here, because here you are entering maybe 10% of the air, 10% of the air there. You still have 80% that must be added later on, and you see that the holes are larger and larger and larger. And also you see these holes for the film cooling. So the air is tangentially entering through here, and radially entering through there. And you see that at the exit, the combustion chamber can have a part of the air that is not yet mixed with the, let's say, exhaust gases. So you see that there is a, let's say, section here between the liner and the external tube that is still containing air that is colder than what you have here in the middle. Okay? This is what we have here is what is called an individual chamber. And you have one chamber, 2, 3, 4, 5, 6, I don't know, 12, 15 chambers like this around the shaft of the engine. They are also called cannular. Sorry, they are also called can chambers, because it has the shape of a can, like the can of the drinks that you are sometimes using. You see the inner side of this system with the video now. I will also discuss the holes that you have there. This is very interesting to understand. And this system is inside the external tube that you have here. So you see, this is the external part of the combustion chamber. And in the external part of the combustion chamber, you have everything that is related with the injector, the fuel injector that you see here in the middle. Of course, if you have 12 chambers, you will have 12 times this, and you will have 12 injectors, one per combustion chamber. And this is inside, like this, mounted inside. And so you see that there is a gap between the external part and the internal part. This is called the flame tube, which is, let's say, a very clear terminology. And so you see that you are like this solving two problems at a time. You are solving, in order to have a very stable and a very good flame in this region, you are solving, let's say, two problems that are the much too high speed that you have and the much too low fuel-to-air ratio by creating a small zone where you have large recirculation, where you have a very low speed and a very high fuel-to-air ratio. Okay? This is sometimes called the primary combustion zone, and after that you can have the secondary and the tertiary, where you are bringing air more and more so that you are leaving the system with, let's say, 100% of the air mixed with the fuel, so the exhaust gases, or that there is a small part that is maybe, as we have seen there, not yet mixed in order to create something specific that I will discuss in a moment. And what is the speed that you have? Of course, it depends because you are bringing more and more air. So the speed will increase. The speed will increase here. So maybe you are in this region with 10 meters per second, 15 meters per second, and then you will increase 40, 70, maybe here 100, and here maybe 150, something like this, because you are bringing more and more air with a constant section, so the speed is increasing. We will see also that the flame will create an increase of the speed. So the flame, the combustion, let's say, will also create a speed increase that I will discuss later on. But the speed is gradually increasing through this combustion chamber. Okay? And you see that we have discussed like this 2 points that are very critical for the entrance conditions. So we have discussed the speed. Let's say it was V2 originally, or you can speak in Mach number. We are at 0.1 or 0.05 in this zone, and this is increasing 0.2, 0.25, maybe at the entrance, and because we are at high temperature, so the speed of sound is very high. And so we have discussed a first point, which is the problem of speed, of Mach number, in the section 2 at the beginning. So we have also discussed the problem of the fuel-to-air ratio. So the speed must, let's say, decrease largely, and the fuel-to-air ratio locally, it must increase. But there is still a problem also of what I have noted there, a third problem and a fourth problem, which is the PT2 and the TT2. Of course, you must have, in order to vaporize, so you will need to vaporize the liquid fuel so that you are getting a gaseous mixture. It is better to have the TT2 that is as high as possible, because the higher TT2, the lower the time you need in order to vaporize the fuel. What about the PT2? The PT2 must be also high, because it will give you a very